Okay, this part of our discussion of thermochemistry, we're going to talk now in more detail about some new pieces. We're going to be looking at how we take a balanced chemical equation and enthalpy change for reaction a little bit more in more examples with enthalpy change per mole, per gram, either one of reactants and products, and how these things are set up and how we look for things like specific heat along the way, and we're going to check for some heat flow. Lots of examples, takes practice. To begin with, we have to describe what a thermodynamic standard state is. A thermodynamic state in the diagram, the box in the center of the screen, shows you that it is the most stable form of a substance at 1 atmosphere, which is ordinary pressure, and at a specified temperature, typically something sort of ordinary like 25 degrees Celsius. And if it's in solution, we'll talk about 1 molar concentrations for each of those substances in a solution. So if we're looking at the process at the top here, that would be propane reacting with oxygen and making CO2 and water. We call this combustion. As you might recall, this is a combustion reaction. And we could look at their 2 different values here. What's the difference between these 2 processes? If you make the combustion reaction occur such that the products are shown as water with a gas, or with CO2 and water as a liquid, which one then is going to be the thermodynamic standard state that is going to be listed as delta H for that process with this little 0 referring to being a standard state? Well, you want to choose the one where the substances are in their stable forms at normal pressure and 25 Celsius. So there's highlighted color here. So is water as a gas or water as a liquid going to be the stable form of water at 25 Celsius? Well, if you think about it, 25 Celsius, water's a liquid. And so the liquid version of this statement is the appropriate one to reflect the process taking place at a standard state. And we have to pay attention to these things. We will do more examples with these gradually. Now, going from that, we'll be using some calculations talking about enthalpies, which is heat changes for physical and chemical changes. The physical changes are simply phase changes, and we kind of make them harder than we need to sometimes. The enthalpy of fusion is, in fact, the amount of heat that is necessary to melt a substance without changing its temperature. In other words, melting ice, for example, takes place at 0 Celsius, where its melting point is, but it takes a certain amount of heat to get all of the the solid water converted to liquid water at that specific melting point temperature. And at 0 Celsius, that would be the heat of fusion that is required. The enthalpy of vaporization is analogous, but this is for vaporization. In other words, converting from, for example, water as a liquid to water as a gas. That's vaporization. And that process is called heat of vaporization. If you convert all of the liquid water to all of it being gaseous, it will take place at a specific temperature, like exactly the boiling point. And the temperature does not change until all of the molecules have been converted from the liquid phase to the gas phase. Sublimation comes up for certain substances, things like carbon dioxide, which is dry ice. And dry ice is a solid, which converts to a gas without so much as ever leaving a puddle, so that's why it's called dry ice. And so we call that sublimation, and there is an enthalpy change associated with that, which would occur at the sublimation point for carbon dioxide. If I've got it in my mind right, it's about minus 78 Celsius, but don't quote me at the moment. I'm not saying that I've got that accurately in my mind just now. Okay, so think about the processes in these diagrams that represent the changes. Fusion is going from solid to liquid, and vapors, that's this one here, and the heat change that's required for that is going from solid in a very orderly array of crystalline molecules to the liquid stage where we have freely moving particles, and the amount of energy to get from the liquid to the gas is the heat of vaporization, where it's all vapor and the molecules are much farther apart now, and definitely freely moving, not influencing one another at all. The heat of sublimation only applies to certain substances, or at least under certain conditions, where you'll go directly from solid to gas. And in fact, for a particular temperature, the change of enthalpy, or heat change for sublimation, is in fact the sum of the heat of fusion and the heat of vaporization. We don't always get to use that, but it's a nice, interesting thing to pay attention to. All right, so let's talk about enthalpies of physical, now chemical changes. So some of these examples have been discussed in class. And this shower of sparks on the right represents this process we call the thermite reaction, where you're reacting aluminum solid with iron 3 oxide, namely rust solid, to make iron solid and aluminum oxide solid. It depends on how you do it. It could be iron liquid. But at the standard state, iron is not going to be a liquid. So this is going to be a standard state value of the heat change. We'll list this as iron as a solid. And the heat change is given you as negative 852 kilojoules. Nobody remembers these numbers, don't worry. So heat is flowing from the system to the surroundings in this reaction, very much showing that in a shower of sparks. The opposite is also evident in another chemical change here. Barium hydroxide that has an octahydrate, we haven't talked about hydrates, but that means it crystallizes with water, can react with ammonium chloride as a solid. And if you do it right, the two will combine to make barium chloride aqueous, ammonia gas, and liquid water. Wow. And there's a positive value, 80 kilojoules in a smidge, for this process. And it's an endothermic process. Heat is flowing from the surroundings into the system. It gets colder, as reflected by the negative value on the temperature display for the device in the picture. So another thing to notice about these things, I showed you the exothermic reaction of the thermite process of aluminum and rust making iron and aluminum oxide, it being an exothermic process. If you could arrange to do it, you could go make the reaction happen in reverse. Let's not worry about the technicalities, how that occurs, but if you did run it in reverse, the enthalpy change for that reaction would be the opposite. Heat would have to flow from the surroundings to the system. You would have a positive enthalpy change to run the reverse reaction. Notice that you're turning iron and aluminum oxide now into aluminum and iron oxide. So the reverse of the first process has the opposite sign for its enthalpy change. So enthalpy is heat, remember. And we think about it as we're looking at heat flow in or out of the system in a process that's a constant temperature. In other words, we don't have closed containers and sophisticated, challenging things to work with. We'll keep it to simpler systems. And these enthalpy changes can be thought about in terms of these simple examples here. Enthalpy going on the vertical arrow, and we're taking solid water and turning it into liquid water. Well, what does that take? It's just like melting the ice and snow outdoors. It takes heat. You have to absorb heat from the surroundings to melt that solid water to liquid, and the value is given here is some number of kilojoules per mole. Don't memorize it, but this would be the heat of fusion. We're melting the water. The other example on the right showed, let's just write it in. And the other example is a process where we're taking methane, remember methane, with oxygen. And oh yeah, if we put methane and react it with oxygen and make CO2 and water, well, guess what? That's combustion again. Combustion does come up in more examples than we think sometimes. And surprise, surprise, it gives off heat to the system, by the system to the surroundings, and the value of the enthalpy change is definitely negative because you're going from the higher energy state of the methane plus oxygen to the products, CO2 and water, and that makes sense in that process. Now let's think about this some more. The change in heat, delta H, is the heat of the products minus the heat of the reactants. And so heat is given off or absorbed during a reaction when we're at constant pressure. And in the left example, water solid turning into a liquid, the heat of the products is greater because it's up here. It's gone, has been increased in the course of the process because heat has been absorbed by the system from the surroundings. And so therefore delta H is going to be greater than 0, a positive value. Notice that we have a positive value for the delta H on that side. On the right, the heat of the products is now less than that of the reactants. And let me see if I can move this diagram a little bit. I'm not sure I can. Okay. So the heat of the products is now less than that of the reactants because this process goes from a higher energy situation of the methane and oxygen to CO2 and water, giving off heat by the system to the surroundings, losing energy. And so in the process of so doing, we have lost energy, and the value of delta H is now going to be a negative value. Always negative when it's losing energy. So let's think, we'll have to do this on a lot of examples because we'll have to stop and think about which way the heat is going. So come back to our methane and oxygen example. Is the delta H going to be negative or positive? Well, if you look at the diagram, you can see that methane and oxygen is higher on that graphical representation than the CO2 and water. So you're losing heat. The system is giving off heat in converting from, here you go, there's your methane and your oxygen to making water and CO2. And the giving off of heat means we call that an exothermic process. And whenever we have an exothermic process, delta H is always going to be less than 0. And for this particular example, it's giving us a value that 890.4 kilojoules are released for every mole of the methane combusted, aka burned, at this typical temperature of 25 degrees Celsius and 1 atmosphere. Now, think about that. Here's the reaction. If that's CH2, methane and oxygen making CO2 and water, and the value of delta H is given as a negative value because it's exothermic, how much energy then is going to correspond to 32 kilograms of methane combusted? Well, remember these values all are interpreted per mole of substances in a balanced equation. So if you have 32 grams of methane, you have to determine the number of moles. So 1 mole of methane, well, carbon plus is 12, 4 hydrogens would be 16. Well, we picked a number for convenience, can you tell? And so that means there's 2 moles of methane, but it's going to be minus 890.4 kilojoules per mole. And if that's the case, all we do is multiply that value times 2 to get a number. If you got your calculator handy, you can figure it out right alongside here and double the value. You get 1,780.8 kilojoules if you have 32 grams of methane. So that's how we use the kilojoules per mole in a simplistic example. All right, we're not done. We need more examples. Keep going. So here's an enthalpy change for the water going from solid to liquid. We're melting the water. Remember, it's got to absorb heat from the surroundings. Is delta H negative or positive? Well, heat has to be absorbed from the surroundings. So heat is being absorbed by the system, namely the water, and that is an endothermic process. Delta H is always going to be greater than 0. The products are higher than the reactants, higher energy than the reactants. So if the value is given to us as 6.01 kilojoules for every mole of ice that melts at 0 Celsius and 1 atmosphere, ordinary temperature and pressure, there's the reaction. What do you think then, with a positive value, how much energy is going to correspond to 36 grams of water being melted? All right, try it out here. So again, this is interpreted per mole as shown in the balanced reaction. So 36 grams of water. Well, let's check it out. What's 1 mole of water? Well, let's see, oxygen still 16, 2 hydrogens more is at 2 more, so that would be 18 grams of water per mole of water. And then we'll look at this balanced equation. Well, it's just 1 of each, so there's nothing to figure out. 6.01 kilojoules per mole of water. And so, again, 36 divided by 18 sounds like 2 precisely. The numbers are chosen for simplicity here. And so it would be twice as much, namely 12.02 kilojoules for 36 grams of water will be evolved. So let's think in terms of how we use these values in thermochemical equations, and there's some nice generalizations here that will help you as you do some calculations. The stoichiometric coefficients always refer to the numbers of moles of a substance. We've done that, but we have to make sure we remind ourselves. And so, for example, if you've got solid water turning into a liquid, you've got the heat change. It's always interpreted per mole. Secondly, if you reverse a reaction, the sign of delta H is going to change, just like I showed with the example with the thermite process. Similarly, with the freezing of water, going from liquid to solid here would have the opposite sign that you have for the melting process. Notice that you go from solid to liquid, that's melting, right? And if you go from liquid to solid, we call that freezing. All right, and the sign of delta H is going to now be the opposite because the process is now exothermic instead of endothermic. And so in the liquid to solid, you get a change in the sign. Don't forget that the sign was positive as you went from solid to liquid. It was an endothermic change. If you multiply both sides of an equation by a factor n, then delta H also changes by that same factor n. So how do we use that? Think in these terms. So if you have 2 moles of water, and you make 2 moles from solid to liquid, then you have twice as many kilojoules evolved, and which is exactly the value we came up with on the previous example with grams as our starting point. One more thing to notice. Physical states of all reactants and products have to be specified in thermochemical equations. If not, you won't necessarily have all the information correct, so you've got to be careful. So we're thinking about solid to liquid in the example of melting the ice, and if we're going from liquid to gas, there you go. You have to specify the phases. This is just phase changes to know what it is you're referring to. And that would be a heat of vaporization instead of fusion in this case. So vaporization has that value. Nobody's memorizing it, but there it is. And the first one is melting, or the heat of fusion. That process. Notice the phases always have to be specified when we're looking at these things. So let's do a couple more examples. The more examples, the better. White phosphorus, there you go. It's P4. It's just called white phosphorus for our purposes. Burns in air, and it's going to make this funny thing called P4O10. So that would be tetraphosphorus decaoxide. Wow. And we're going to try to determine how much heat is evolved if you've got, pick a number, 266 grams of white phosphorus, P4, burning in air. The reaction process is shown here. If you look at it carefully, it's clear, indeed, a balanced reaction. The phases are not shown for the P4, but that's a solid. Don't worry, that's not important to our discussion at the moment. And the burning in air creates a different solid, the P4O10 tetraphosphorus decaoxide. What do you need to know to find how much heat is evolved for that number of grams of white phosphorus? So we're thinking about heat changes, and we're looking at delta H values for a process, but then it's going to be per mole, right? And so we're going to look at delta H, and then we'll have to determine the number of moles, because this is going to be in kilojoules probably per mole, and we'll find the number of moles from the grams using, what do we do to get between grams and moles? Molar mass. All right, are you ready? Here goes. So there's the reaction, the delta H value. You find it somewhere, somebody provides it. You're not going to know the numbers. And then we're going to look at the 266 grams of the phosphorus, P4. And, well, then what do we have to do? We have to come up with the number of moles. So the molar mass is there. Thankfully for us, somebody punched it in for us, but phosphorus is essentially about 31 grams per mole. And times 4, you get that. It's almost 31. And so you multiply that out, and you get 123.9 grams of phosphorus per mole of P4. And so after that, we take our 3,013 kilojoules per mole of P4. Notice that it's for 1 mole of P4 here and 1 mole in that relationship. And when we set this all up correctly, things should cancel out. The P4 grams will cancel out. The moles of P4 also cancel, and you get a value of, plug in the numbers, 6,6470 kilojoules for that process. Notice this is just an exercise in making sure you've set things up so that units will actually cancel, recognizing that our enthalpy of this reaction process is described per mole of the reactants involved. Let's do another example using some of these relationships that are generalizable and helpful. If you know that sulfur dioxide reacts with 1 mole of sulfur dioxide reacts with half a mole of oxygen to make sulfur trioxide, and you have a delta H of the reaction at the standard states, that's what that little 0 superscript tells us, and you're given a value minus 99 kilojoules per mole, we're going to ask to find the enthalpy change, delta H, for the reaction shown below. What do we have to do? Well, first of all, what can we know? If you take the reaction as shown, you have twice as much as the reaction above, and it's also in reverse. So delta H for this process, instead of being negative, will be a positive value, and it's also going to be for 2 moles of SO3, a whole mole of oxygen, and 2 moles of SO2 instead of a single one. And so your delta H will correspond to be twice as much. And so what is it going to be? It's going to be 99 times 2. And if you can do your math, that looks like 198 kilojoules per mole as shown in this reaction. So the sign changes because the reaction is in the reverse direction, and it's twice as much as the original reaction, so you multiply it times 2. Not so bad. Let's try one more example for this recording. Let's look at sulfur dioxide again, and we're making it the way we looked at it a minute ago, but in the reverse this time. So how much heat is evolved if 320 grams of SO2 is burned according to the chemical reaction equation shown below? Well, now what do we do? We've got the same process of SO2 combining with oxygen to make SO3, but this time we're going in the exothermic direction so that the heat released is a negative value, but we're going to start with 320 grams of SO2. What do we need? Well, we need to find out how many moles of SO2 is involved. So start with your 320 grams of SO2, and to get to moles, 1 mole of SO2, get out your handy calculator and check out the values. So sulfur is, the molar mass of SO2 is going to be, sulfur is 32, oh handy, and 2 oxygen is 32, well that's going to be 64 grams per mole. Nice value to know, 64 grams of SO2 per mole. So far so good. But that tells us how many moles of SO2. But this heat of the reaction, the enthalpy change for the reaction, is per mole of everything as shown in the balanced equation. And so this is going to be used how? It means it's minus 198 kilojoules per, in this case, 2 moles, based on our balanced chemical equation, 2 moles of SO2. And what else is lacking? So we should be able to cancel out moles of SO2, and we will end up with the heat evolved for the process by completing the arithmetic, by doing the math. If you can do your math together, you'll be all good to go. So plug it into your calculator and try it out. I would like to simplify when I do these kinds of things because that's my mindset, and you can too. You can take 2 out of the bottom if you turn this into 160. And if you know how many times 4 goes into each of these numbers, 4 goes into 64, 16 times 4 goes into here 40 times. And how many times does 4 go into 40? It would be 10, and 4 goes in here 4 times. So now we've simplified it. So the top is going to be, I'm just doing this without a calculator, so you're there, 1,980 divided by 4, which is also equivalent to what you would have done without the simplification steps. And the answer is, I hope you tried it with me, and the answer is 495, oh, but don't lose the negative sign, minus 495, what's the units? Kilojoules for this process. It is heat released. Oh yeah, we're burning. So this should be a negative value for the delta, the heat evolved for this process. Okay, a lot of examples, a lot more to come, but I hope these get you a good start. Good luck working on your assignments. Ask more questions as needed. I'll see you in class.